Hello and welcome to this PIR live event brought to you by Partners in Research Canada. My name is Stacey Joyce and I will be your host. Please remember that you can ask questions if you're joining us live throughout the entire webinar, and we will just queue them up for the Q&A portion at the end. If you do ask a question, make sure that you include your name, your school, or your city so we can give you a shout out when we ask it on your behalf. And I will now introduce you to today's guest. We have Dr. Richard Léveillé. He is an adjunct professor in the Department of Earth and Planetary Sciences at McGill University. He's also a professor in the Department of Geosciences at CEGEP John Abbott College. And he is also a participating scientist at the NASA Mars Science Laboratory. Thank you so much for joining us. I will let you take it away.
All right, thank you very much, Stacey, and welcome everyone. It's great to see people from all across Canada. And I will get right into fun pictures. All right, so today I would like to talk a little bit about Mars exploration and talk about working with the Mars Science Laboratory Curiosity rover, and a little bit about a new project and a new endeavor we've embarked upon, and that is to look at something we call lava tubes, which, well, we can visit here on Earth, and hopefully someday we can visit on Mars. So, okay, so here you should be able to recognize a couple of planets here. The one on the right should be most familiar with you. Of course, that's Earth, with all its blues and greens and browns and white clouds. So a very active, dynamic planet with, of course, lots of liquid water, lots of life, lots of vegetation that we can clearly see in the green colors and so on. And then there's little Mars, which is about a third of the size of Earth. It's one of our neighbors, along with Venus, but we'll focus on Mars today. And Mars, as you can see, is quite a bit different from Earth. It doesn't have any liquid water at its surface, doesn't have any obvious vegetation, doesn't have any obvious life for that matter. There is, we can't quite see it on this picture, but there is ice, including ice water at the north and south poles that we can't really see on this image. So Mars is a very cold place and a very dry place, so very, very different from Earth. But perhaps, and scientists seem to think now, that Mars used to be quite different. So in its early history, Mars was a warmer and a wetter planet and has gone through large-scale changes over the course of its history. So I'll talk a little bit about that today, and I'll show you how Mars may have changed a little bit in its appearance. Of course, Mars has that characteristic reddish color, and you may have even seen it yourself, because on some nights you can see Mars in the night sky. It looks like a reddish star to the naked eye. So I invite you to check that out if you haven't already. Okay, so Mars, being one of our neighbors, is a busy place. It's also scientifically very much of interest. So there's a lot of traffic at Mars. So right now on the surface of Mars, there are two robotic rovers on the surface. So the Opportunity rover that you can see there on the upper left, and next to that is the Curiosity rover, which I'll be talking about a little bit more today. And then we have a number of satellites that are orbiting Mars, including US satellites, a European satellite, even a satellite from India, which is now in operation around Mars. And all of these missions are seeking to answer various questions about the history of Mars, how it's changed over its time, what is the atmosphere composed of, how has the atmosphere changed, and perhaps the biggest question of all is, was there ever life on Mars? Okay, let's focus on Curiosity now. So Curiosity is a US rover. It's part of the Mars Science Laboratory mission that NASA operates in the US. The rocket was launched in November of 2011 and traveled 544 million kilometers over about 8 months to get to Mars. So Mars, even though it's one of our neighbors, is quite far, and it takes several months to get there, even with our modern rocket ships. So Curiosity, luckily everything went well and landed on August 5th, 2012. So we're going on the 5th anniversary of Curiosity landing on Mars. And as you can see on landing night down and below, everyone was very happy, very excited about the successful landing of Curiosity. Okay, so the mission is called the Mars Science Laboratory, and the rover is called Curiosity. Why is it called the Mars Science Laboratory? Well, it's really a laboratory on wheels. So here's a cartoon of Curiosity with 10 of its instruments. So it has 10 science instruments, all designed to look at different things: the chemistry of rocks, the mineralogy of rocks, what minerals are present. Some instruments are characterizing the radiation, how it may be harmful for future humans who may go there. There's a weather station, all kinds of instruments, in addition to all the wonderful cameras. And of course, one of these instruments, drum roll please, is Canadian, and that is the APXS instrument, which stands for Alpha Particle X-ray Spectrometer, which you probably won't remember tomorrow, but that's okay. So Canada has contributed one of the instruments to this mission, and there are, of course, a number of Canadian scientists and engineers working on the mission, alongside a number of US colleagues, of course, and also a broader international team. Okay, there's one of Curiosity's favorite popular selfies, if I may say. And so these are images that are taken every once in a while. It's actually a mosaic of several tens of images taken by a camera at the end of the arm, and it points back towards itself, and then someone goes and stitches all those images back together to form a mosaic. And while this is maybe just an interesting selfie of some sorts, it's actually useful because the scientists and engineers on the team can look at the rover, look at all the different parts and see if everything's working okay. And also we get to see all around the rover, and we can help to, we can use this information to help understand what the rover is seeing, and also to plan what we'll do next with the rover, and sort of where we'll drive to or what rocks we may want to analyze. Okay, so working on Mars is a little bit complicated. Now, if you've seen the mission, The Martian, or sorry, the movie, The Martian, this is explained well in the movie. So Mars is quite far away, and of course has a bigger orbit than Earth. So it goes around the sun about every 23 months, as opposed to us. We go around the sun in 12 months, or 1 full year. And so Mars is often quite far away from us. And so even at the speed of light, our signals, when we communicate with Mars, take anywhere between 4 and 20 minutes to reach their destination. So we can't be in live contact with Mars all the time, so we can't drive the rover with a joystick as if it was a video game, but we have to send signals to Mars, and then the rover executes those commands and sends us information back, measurements from the different instruments. It sends us pictures and information on the status of the rover itself. So it's a little bit challenging to work on Mars, but nevertheless, it's very exciting. Okay, so this gives you a planetary view of Mars, and with a number of locations where we've actually touched down on the surface with either landers or rovers. So there's a few places going all the way back to the Viking mission in the 1970s, and up to Curiosity, which is the latest mission to reach the surface of Mars. And so over on the right there, you can see where Curiosity landed, about at the equator of Mars. And Curiosity landed in a large crater called Gale Crater, which is a large impact crater. So it's a big hole dug in the ground by a meteorite impact many, many millions of years ago on Mars. And you can see down below there's an oval, which is the target, basically, where Curiosity was supposed to land. And Curiosity did successfully land in that area called the landing ellipse, and has since been exploring that region of Gale Crater. And in the middle of Gale Crater is a large mountain called Mount Sharp. And that's part of the reason why Curiosity was sent there, was to investigate the lower reaches of Mount Sharp. Okay, some pretty pictures. Here's one of the first mosaics, a color mosaic of where Curiosity landed. So you can see the shadow of the rover, and you can also see Mount Sharp in the background there. Curiosity used a, some would say, crazy contraption called the sky crane to land. And if you want to learn more about that, I invite you to go onto YouTube or onto NASA's website and check out the movie 7 Minutes of Terror, because that's how long it takes to go from the top of the atmosphere to the surface of Mars. It takes about 7 minutes to slow down. and is a bit of a nerve-wracking time for the people working on the mission. But luckily, Curiosity succeeded in landing and has been returning wonderful images like this one. So this is a rock called Link. So us scientists, we like to give names to the rocks on Mars. This one's called Link. And this is what we call a conglomerate. So you can see, for instance, on the upper left, you can see some rounded pebbles. These are characteristically found in rocks on Earth that have been transported, or sediments that have been transported in moving water, such as in a stream or river. So this is a rock that tells us a story. And in fact, all rocks tell stories. And of course, geologists are experts at telling those stories. So this rock tells us many, many years in the past, and we're talking over 3.5 billion years. So in the early history of Mars, this rock tells us that we had flowing water at this location. So not necessarily a lake, but actually a stream or a river. Now, if we go further, or as Curiosity went further, it came across different kinds of rocks, of course. And this is a location called Yellowknife Bay. And you can see the series of images here showing you the arm, the robotic arm, which is being placed on the surface of the rock. And Curiosity has a little drill, and it can drill into rocks as it's done here. And you can see on the right the little drill hole. And it's able to collect the rock powders from that drilling and bring them into instruments on board and do all kinds of useful scientific measurements. And in this case, it was interested in looking for organic molecules and telling what kind of minerals are present in this rock. And this rock became known as John Kline. And you can see that on the right, you can see the outside surface is characteristically red, which is the color you think of when you think of Mars. But in fact, that red color is from a coating of fine-grained dust, which is composed of iron oxides, kind of like rust. When a piece of metal, like an old car, rusts, it sort of gives that reddish color. So Mars is covered by this dust, which is rich in these iron oxides, which are kind of give it this rusty color. But in this case, the rock is actually gray in color on the inside. So these kinds of rocks, this last rock, this would have been a fine-grained deposit deposited in a lake environment. So we have evidence of rivers, we have evidence of lakes. And so we can imagine at one time in this large impact crater, we had liquid water, which created a lake and which deposited the sediments, which went into forming the rock that we just looked at, the John Kline rock. So obviously, Mars in the past was very different. And so a picture is emerging now, not only from Curiosity, but from other missions, that we've gone from a very wet and perhaps warmer Mars, as you can see on the left, to Mars today, which is very much dry and much less hospitable to life as far as we know. So when we're talking about looking for maybe traces of life on Mars, we're probably looking in the distant past, so in rocks that are very, very old, i.e. about 3.5 billion years old or more. So rocks from the early history of Mars. And so the rocks of Gale Crater and Mount Sharp reveal what we call habitable environments. So environments that could have been habitable at the time. So places that were warmer than they are today, which had liquid water. So these are things that we think life requires. And so these environments would have been habitable. And of course, us geologists are busy reading these rocks on Mars. But as of yet, we haven't found any evidence of any of these environments having been inhabited. So there's been no evidence of actual life on Mars, despite what you may have read online in some websites. So no scientific evidence of life on Mars yet, at least not in the places we've looked. So which brings me to the next part of the presentation, and that is to focus on lava tubes. And perhaps this represents a subsurface environment that we can study eventually on Mars, which may hold some evidence of what went on Mars in the past. So we're exploring lava tubes on Earth. Here's an example from Lava Beds National Monument in Northern California. And lava tubes are pretty common in volcanic regions on Earth, places like Hawaii, Iceland, of course, California, Canary Islands, all kinds of places like that. Wherever you have what we call basaltic volcanism, and there's a little series of cartoons on the left that describes how a lava tube forms. So these are subsurface cave-like conduits that form as lava cools on the exterior. So the molten lava starts to cool, it becomes hardened, and you form like a shell on the outside, and things remain warm, the lava remains warm in the inside, and it keeps on flowing, and you eventually get left with basically a hollow tube or a hollow cylinder, and this is known as a lava tube. And on the right, there's a picture there with some of the features we commonly see. So you could have an opening on the side, you can have collapsed trenches, and you can have skylight openings or entrances, which are kind of interesting. And we think that there are lava tubes on Mars as well as the moon, but I'll focus on Mars. So here are some pictures. So we see these sinuous forms with collapsed parts to them. And we see, for instance, in the middle, we see what we think is a skylight opening to one of these subsurface caves, and zoomed in on the far right there. So these are likely lava tubes. We would like to get into one of these, but we haven't been able to yet, or we haven't really tried. So these are pictures from satellites, and we're trying to guess what might be on in the subsurface. And the subsurface, or in one of these lava tubes, the environmental conditions, so the temperature, the wind condition, the radiation, the amount of radiation that is coming from space, these are all going to be different from what's on the surface. So they may represent a more protected environment and maybe more hospitable to life. So here's some more pictures. So some lava tubes are big, and there's a student, Jenny from McGill. And some lava tubes are quite small, but they're all of interest to us. And so we're busy working in some of these lava tubes here on Earth and trying to learn about the composition of the rocks, the waters that are found in them. Some of them have ice, so we're interested in looking at what may be found in the ice. Are there any microorganisms in the ice that may be preserved? And so we're taking samples, we're doing measurements in these caves with portable instruments, and we're looking at what microbes may be there. And of course, looking towards the future, as you may know, there's a lot of talk of humans going to Mars. Well, humans are going to need to, and you may recognize Matt Damon there on the left from The Martian, or a picture from the National Geographic series on the right. And humans are going to live somewhere, and one of the places where they may set up their shelter is in one of these lava tubes, which would offer some natural protection from the elements on Mars. So that's looking further into the future. And I will stop there, and I'll leave you with a sunset in Gale Crater taken from the Curiosity rover. And I'm sure you have all kinds of questions, so I would be happy to answer them.
Thank you so much. I find it quite curious how this image of the sunset seems very dark. It almost, is there an atmosphere or something that's making it fuzzier there?
Well, there is an atmosphere on Mars. It's not a very dense atmosphere. It's not as dense as on Earth. I'm not sure exactly how these images. There's always some processing involved in imagery from not only from Mars but from other planets or any space image. So I'm not exactly sure how this was processed. So I'm not sure. I guess it's just a low light image that maybe they had to stretch the contrast a little bit with.
Yeah. Okay, well, I guess I had to stick in one question from me there, but let's move on to questions from our audience and the students out there who are watching. So I have our first question here from the grade 3s at Hawkwood in Calgary, and they wanted to know how big that crater was. So you showed that one crater that we thought was maybe a skylight to a lava tube. Do we know how large that is?
So the skylight opening was on the order of, that one was on the order of, I think, about 100 meters. And that may seem big. And in fact, some of the lava tubes on Mars and also on the moon appear to be quite bigger than the ones on Earth. And that could be due to properties of the lava eruption, but also of the lower gravity. So as you know, Moon and Mars have lower gravity than on Earth. On Moon, it's about 1/6 of what Earth's gravity is, and on Mars, it's about 1/3 of what Earth's gravity is. So for instance, an astronaut who weighs, say, 180 pounds on Earth will weigh 60 pounds on Mars, so 1/3. So it's instant weight loss program. So the gravity can actually affect the size of the, it's thought of the size of the lava tubes. So we think they're probably at least the ones we can see, maybe they're easier to see, we think there are quite large lava tubes on Mars. So that one I think is about 100 meters in size.
Interesting. So we have a sort of related question from Jeff in Woodbridge, Ontario. He's asking, does that mean that there are volcanoes on Mars?
Absolutely. There are clear volcanoes on Mars. Most of them are, we think, extinct today, or all of them are believed to be extinct. They have been active in the past. In fact, we can see some very large ones. In fact, Olympus Mons is considered the largest, if not one of the largest volcanoes in the solar system. So definitely bigger than any volcanoes on Earth. And part of that explanation is due to the fact that you have magma coming from the subsurface of Mars. But on Mars, there are no plate tectonics like on Earth. So there are no plates moving at the surface of Mars. And so all that magma, when it reaches the surface, it kind of keeps erupting at the same location. And the volcanoes can grow up to be much larger than, say, the Hawaiian volcanoes here on Earth. And we think the most recent volcanism on Mars, the most recently active volcanoes on Mars were about 1 billion years ago. So still quite far in the past, but geologically that's getting to be almost recent.
It's amazing how that can be recent in geology terms, but that seems like so long ago, how we normally think of time.
Yeah.
Our next question comes from Ms. Payne's grade 5s and 6s at Allenby Public School. They wanted a little more information about how lava tubes might be related to life on Mars.
All right. Well, we can only speculate, but we know on Earth, all lava tubes, once they cool down and once you get water trickling down from the surface and into these lava tubes, you have all kinds of microbial life, quite diverse microorganisms. They form typically biofilms on the walls and ceiling of these cave-like structures. And so we know that exists on Earth. And we know on Mars that these lava tube environments would offer some protection. And one of the main hurdles, if you will, to life on Mars is the radiation at the surface. So Mars is not as protected as Earth is, so there's less atmosphere and there's no magnetic field, at least not today. So there's less protection from radiation, from UV radiation. So for instance, here on Earth, in our upper atmosphere, in the stratosphere, we have the ozone layer. And the ozone layer protects us a lot from UV radiation. Some UV still gets towards the surface, and that's why we put sunscreen on in the summer. And but on Mars, it's much worse. So there'd be much more radiation. And whereas if you're in the subsurface, you're in a more protected environment. The temperatures can be more stable, so you have less of these crazy fluctuations. On Mars, it can be typically minus 85 degrees Celsius. That's pretty cold. Whereas in one of these subsurface environments, the temperature could be a little bit more stable because of, it's a little bit complicated to describe the physics, but you can get certain air circulation restrictions that create a more stable environment. So because of these reasons, because we think of it as a protected environment, we think there could have been life that existed there in the past, and the traces of that life, or what we call biosignatures, may be preserved in some of these lava tubes, and we can go investigate those today. There are some people who speculate maybe there's even life today. I tend to think that if there's ever life on Mars, it would have only existed in the early history of Mars, and perhaps we have some kind of preserved fossils or preserved remains of that life that may exist in one of these lava tubes.
Lots and lots of speculation at this point, it seems. Yeah. And if I could just ask you, Dr. Léveillé, to click the stop share button, we'll be able to see you a little bit larger rather than a tiny little picture while we see the sunset.
All right, there you go.
Awesome.
How's
okay,
that?
Perfect. So our next question then is a long one, so bear with me here. From Ms. Brothers' class, they're grade 9s at Notre Dame in Ottawa. Is it possible that if we were to give back some sort of gravity to Mars and decrease the amount of solar waves hitting Mars, that we could melt the water or ice on the surface and restore its previous form?
So Mars never had more gravity. So gravity is related to the mass. And so Mars is a smaller planet. It has about 1/3 of the mass as Earth, and therefore it has about 1/3 of the gravity. So it hasn't really lost any gravity. It has lost some of its atmosphere. So some of the gases in its atmosphere have been lost to space over time. And some of those gases could be greenhouse gases, like for instance, CO2 or maybe even methane. And of course, those gases, being greenhouse gases, exert a greenhouse forcing and can exert warming on a planet. Just like on Earth we have greenhouse gases. On Venus, there's an extreme case of greenhouse gases where there's lots and lots of CO2, which makes Venus super hot. In fact, the surface of Venus is about 450 degrees Celsius, so super hot on Venus. Mars doesn't have that nice warming greenhouse like on Earth, or nothing like Venus, and plus it's a little bit further away from the sun. So that's the main reason why Mars is colder. And so I don't think the gravity is the solution, but people have invoked different ways of increasing greenhouse gases in the atmosphere on Mars to maybe make it warmer and bring it up to a more clement temperature. So I should know that on Mars, occasionally, in some days, so for instance, there are seasons on Mars during the summer months near the equator. On a warm day, you can get above 0 degrees. So the temperature will rise a little bit above 0 in some locations on some days at some times of the year. But in general, it's a very cold place.
Perfect.
So I think that covers the answer to that long question.
Yeah, my next challenge here is to get 2 questions answered before one of our viewing classes has to leave us. I think their class period is ending. Okay. So from Brantford, Ontario, the grade 9s in Ms. Spicer's class want to know, how did you get the picture of Mars that looks like Earth, so the way it maybe once was?
So that's an artist's rendition, or just a drawing by someone who imagined what it might look like. So that's not a picture, it's not a photograph. I should have mentioned that. Good point.
And how do you date the rocks on Mars? That also comes from our grade 9s in Brantford.
That's a very good question. It's a little bit complicated, but one of the traditional ways we do that on planets like Mars and the Moon and Mercury, the innermost planet, is we look at the number of impact craters on the surface and the sizes of those impact craters. And we have an idea of how many impacts there were in the inner solar system throughout the history. And so we can kind of use the number of craters and the size of craters to give us an idea of the age of that surface. And so we call that crater counting. And in the case of Mars, with Curiosity, some really smart scientists were able to take measurements from 2 different instruments. One measurement that measures potassium and another instrument that measures argon, so 2 different elements. And using those 2 measurements, they're able to come up with an age, because we know that some elements are radiogenic or radioactive, and they decay into other elements. And this happens on Earth, and this is a typical way that we use to date rocks on Earth. So the potassium-argon method of dating is a very well-known method, and this was the first time it was used on another planet. So that's pretty exciting. And this may sound foreign to you, but you may have heard of carbon-14 dating. That's kind of a similar process, but carbon-14 dating can only be used for things containing carbon and things that are relatively young, generally about 50,000 years or less. So similar process applied to much older rocks. So the age of the rock that was dated with Curiosity gave an answer of about 4 billion years old. So very old rocks.
Excellent. I'm just trying to decide which of these questions to ask next here. Samantha in Woodbridge would like to know, what are the most common types of rocks on Mars?
Well, that's another good question, and I would say we don't really know yet because we've only been to a few places. But traditionally, we've thought of Mars as being very much influenced by volcanism. So we talked already about volcanoes. So people have thought, well, there's going to be a lot of volcanic rocks. or igneous rocks, if you guys have studied rocks. But when Curiosity landed, right away the rocks looked a little bit different, looked a little strange, and when we started looking closely at them, we found out that they're predominantly sedimentary rocks and rocks that were deposited in water. So for instance, the conglomerates I showed you a mudstone, a fine-grained mudstone. There's also lots of sandstones. So again, rocks that are deposited in moving water or perhaps in beach-like environments or deltas. So the story within Gale Crater, at least, and the story of Mount Sharp is a sedimentary story. So we're seeing rocks that are mainly sedimentary rocks. And for the most part, these rocks are similar to rocks that we can see in different places on Earth. So we can compare and contrast what we know about geology on Earth and rocks on Earth, and we can try and use that to understand what we're seeing on Mars. And we're not seeing anything all that strange or all that different from what we would see here on Earth.
Interesting how similar they can be from a geology perspective.
Yeah. We often talk about the laws of physics and the laws of chemistry being the same all across the universe. Well, same thing with geology. So we would expect perhaps similar processes forming, minerals, forming rocks, forming volcanoes, mountains, and so on. Mostly similar, perhaps maybe with some individual differences depending on where we are and what the conditions are at that particular location.
Interesting. Next, I want to go to another question from the grade 5s and 6s at Allenby Public School. They want to know, is there any way that Mars could be terraformed?
Yes. Well, yes to the question. I don't know if the answer is yes. So terraforming, for those who don't know, is the idea of making Mars more perhaps Earth-like, i.e., warmer, perhaps with some kind of life. And people have proposed all kinds of ideas. For instance, Mars has CO2 in the atmosphere. Well, we could perhaps plant a plant of some sort or a green algae, and that organism would use the CO2. And what do plants produce as a byproduct? Well, they produce oxygen. And so that could be one way to produce oxygen on Mars. Of course, we'd have to do it at a large scale for oxygen to build up, because right now there's not much oxygen in the atmosphere, certainly not enough for humans to breathe. So that's one idea. Other ideas have, actually there's a whole range of, some would say crazy ideas on how we could make Mars warmer. People have a bunch of nuclear bombs and detonate them, and that would make the planet warmer, but I don't think we're about to do that anytime soon. So it's a common idea that people talk about, but we're nowhere near doing anything to terraform Mars. And I think for a long time, humans who may go to Mars, we talk about this a lot these days, humans who go to Mars, they'll have to be, in spacesuits, protected from the elements. They'll have to have their breathing apparatus, et cetera, all the protection from radiation and so on.
So on a related note on radiation, Ms. Falconer's class wanted to know, if we lived on Mars, would solar flares harm us?
Yes, potentially. That would be one of the risks. There's the normal solar wind, so particles that are coming from the sun that could be harmful. In addition, we talked about the UV radiation and so on. So yes, these are all hazards or risks, and humans would need to be protected both in the spacecraft as they fly towards Mars, and wherever they may stay on Mars, whether it's in a structure of some sort, or perhaps tucked away in one of these lava tubes.
Perfect. The students at Notre Dame in Ottawa have been patiently waiting for me to ask their question. They'd like to know what Maven stands for.
Maven stands for, I believe, Mars Atmospheric Volatile Environment, perhaps. I'm not sure exactly. I'll have to double check that. But I would invite you to look it up. It's not too hard to find. Just go to NASA's website. So Maven is a fairly recent NASA mission that it's a satellite. It's orbiting Mars, and it's mainly studying the atmosphere of Mars. So what gases are present in the atmosphere, whether we can talk about a greenhouse effect and things like that. But I'm not sure of the acronym. Lots of acronyms in space.
It does seem so. Next, we have a question from more grade 5s and 6s, this time at Lincoln Alexander in Hamilton. Do the ozone layers on Mars have a stronger effect on the sun than the ozone layers on Earth?
So, in fact, there's no ozone layer on Mars, which is one of the problems. So the ozone layer on Earth keeps us protected, fairly protected from mainly from UV radiation from the sun. On Mars, there is no ozone layer, and that's simply due to the fact that ozone is an oxygen molecule. It contains 3 oxygen atoms, and it's formed from the breakdown of oxygen molecules, molecular oxygen, which we call it, which contains 2 oxygen atoms. And those 2 oxygen atoms are bonded together in a molecule, and with the sunlight, with UV radiation, they break apart, and then they can recombine as 3 oxygen atoms, which is an ozone molecule. And ozone has the property of absorbing UV radiation. So on Earth, we have ozone because we have a lot of oxygen. As you know, the Earth's atmosphere has about 21% oxygen. And so that some of that oxygen reacts and forms ozone in this layer up in the what we call the stratosphere, in the upper atmosphere. On Mars, there's no oxygen or very little oxygen, and so there's no ozone. So we don't have that natural protection on Mars that we do here on Earth. So we would need to be more protected on Mars than on Earth. And just adding more sunscreen won't do it. We'd need to have protective spacesuits and protective habitats or shelters.
Okay, so we're going back to Curiosity now. And Ms. Goulet's grade, we have grade 4s in Bragg Creek, Alberta, who would like to know if Curiosity can operate at night or in the dark. And they're wondering this because they wondered if we would need a new rover designed to explore the lava tubes.
So I'll maybe answer the last part. Definitely, there's no plan for Curiosity to go into any lava tube. In fact, there are no lava tubes anywhere near Gale Crater. So that's not that part of Mars. It's not a volcanic region. So any mission to a lava tube would go somewhere else on Mars. Of course, we'd pick the location beforehand, and it would most likely be with a very different rover. So one that would be maybe more designed to move over rocks and boulders rather than just roll on a smooth surface. Because some of these lava tubes can be quite rocky and quite hard to get into if you're a rover. The other part of the question is yes, technically Curiosity can operate at night. The problem at night on Mars is it gets very, very cold. Okay, so the temperature drops a lot on Mars overnight, and any motor or engine or of any sort is harder to work at night. And if you've ever been outside with anything battery operated in winter, batteries, they drain faster at cold temperatures. So generally what happens is Curiosity operates during the daytime and overnight kind of relaxes, sleeps a little bit. It sometimes takes a few night pictures because it has a camera with UV lights, and those are pretty neat. And it shines the UV light on rocks or sediment. And but generally it doesn't operate at night because it's just too cold. And for instance, if we were to move the arm actually has heaters. The robotic arm has heaters because it can't easily move at minus 20 degrees Celsius, so it has to be heated up. And typically, on a given day, the arm won't be moved until about noon on Mars time, when it gets a little bit warmer than in the early morning. So it doesn't have those hard constraints of not being able to work at night, but because the conditions are more difficult, it rarely does much at night other than take a few pictures or take some measurements with some of its instruments. But it never drives at night, and it doesn't use its robotic arm at night.
Interesting. I wouldn't have thought of that. Thanks for that question. One more question about life on Mars. We had two different classes who were curious about whether life on Mars would be more or less evolved than life on Earth, and perhaps would anything have been similar to life on Earth, you know, the 3.5 billion years ago that you were talking about?
Well, again, we can only speculate because we have no clear evidence of any life on Mars. So that's a possibility. It's possible that there was never life on Mars. If that's the case, we can ask ourselves, well, why not? Because, you know, conditions seemed habitable in the past. You know, we had these little lakes and sort of clement conditions for life. But because there's no obvious life and abundant life and diverse life like we see here on Earth, I don't think many people believe that there was anything much more than microbial organisms on Mars, if at all. So we're probably talking about some kind of microbial life that may have existed probably in the distant past when conditions were more habitable or more hospitable to life. And then things got too cold, too dry with time, and life kind of fizzled out if it existed there to begin with. So generally, when we're talking about life on Mars, at least most scientists think that maybe there was some kind of, you know, bacteria or simple life forms early on in the history of Mars, and we might find evidence of those in some of these very old rocks. That being said, there's a few other people who have a few other ideas, and there's some evidence of maybe some salty water being liquid on Mars even today. Maybe you could have some salt-adapted organisms living in these strange locations. But again, it's not plentiful. It's not abundant because we don't see these trees on Mars. We don't see elephants walking across the front of the rover's camera. There's nothing really obvious. So if anything, it's very restricted into specific locations, or may have only existed in the distant past. But again, it's speculation. If you want to imagine some crazy alien on Mars, you can, but there's certainly no evidence of that yet. Right.
And so I can't believe we haven't received this question yet, but I'm going to ask it on behalf of our viewers who will watch this recording later. How did you get involved in the team that's working with Mars Curiosity rover, and sort of what path have you taken to where you are today?
Good question. So I actually have my university training or degrees are in geology, and so I know all about minerals and rocks and fossils, and in fact I also studied a lot of biology when I was at university, and so I've always had this interest in how biology may affect geology. And so, for instance, we know that there are bacteria that can degrade rocks, or they can help to produce minerals. And so I studied geology. One thing led to another. I ended up working at the Canadian Space Agency, just here nearby Montreal. And so I was interested in space stuff in general, space exploration, planetary missions, and so on. And I was working, doing research in places on Earth that can inform us about things on Mars. So for instance, in lava tubes, I got to work in the high Arctic, went to Hawaii one time to do a project there. And so these are places that are not exactly like Mars, but they may resemble Mars in some ways. For instance, they may be very dry or very cold or have similar rocks. And so we can study them here on Earth, you know, in the meantime, while we're waiting to get to Mars with a mission, or to get some data from Mars. And then for the Curiosity rover and the MSL mission, basically NASA had a call for scientists to propose ideas to join the team. So that's what they call the Participating Scientist Program. So I sent in a proposal to NASA, and it was selected. And so I've been a part of the team ever since. And there are 2 other Canadian scientists are in the same position as me. And we get research funding from the Canadian Space Agency to work on the NASA mission. And of course, we work with Canadian students and graduate students mostly, and at universities, including at McGill, where I'm affiliated with. And so we participate in the operations of the mission, in selecting the targets that the rover is going to analyze, and in interpreting the data and the images that the rover sends back. So yeah, so it's definitely a possibility. There are other ways of joining emissions. So for instance, I mentioned earlier the APXS instrument, which is a Canadian instrument. So that's led by a scientist at the University of Guelph in Ontario. And so that instrument has a team of experts who know that instrument very well, and they are also working on the mission. And of course, they focus perhaps more on that instrument, but they contribute to the data analysis, interpretation, and so on. So the broader mission team is composed of all those instrument teams, a bunch of participating scientists like myself, and then a few engineers and scientists that have various expertise and capabilities.
And would you have, just to finish out today, would you have any advice for students who might think all of this is interesting and maybe they wanted to pursue a similar path?
Definitely. There's a number of ways. So I work with, of course, geologists, there are biologists, there are chemists, there are physicists, there are all kinds of experts, engineers, of course. I know one Canadian who's an engineer, and he works now at NASA Jet Propulsion Laboratory in California. And he's working on a software package that Curiosity uses to automatically target certain rocks. So for instance, after the rover drives on a given day, it can stop, it can look at the scenery with its cameras, and it can decide itself, so it's kind of a type of artificial intelligence almost, it decides on the rock that looks most interesting, and it fires its laser instrument, the ChemCam instrument, fires its laser at that rock to get like what we call an extra analysis. Otherwise, we would have had to wait to get the images back here on Earth. Scientists would have had to discuss it, would have had to tell the rover, okay, shoot at that interesting rock. But now with this new software on board, the rover is able to do an extra analysis all by itself on whatever it thinks is the most interesting rock. So it could be a rock that looks a little bit different than the other ones. It could be the biggest rock or the brightest or something like that. So there's all kinds of ways to get involved. I think you have to find out what interests you. If you're interested in rocks and minerals, of course, you got to go study geology. If you're interested in biology or chemistry or physics, atmospheric physics, there are people on the Curiosity mission who are experts in radiation, who are experts in winds, people studying sand dunes. There's all kinds of things to study, and all kinds of people with different expertise working, generally working all together on the mission.
Excellent. Well, that is all the time we have today. We're actually a couple minutes over. Thank you so much, Dr. Léveillé, for joining us today and answering all of our questions.
All right. It's my pleasure. And thanks, everyone, for the great questions. And I hope you enjoyed it.
Perfect. Well, next on PIR Live Event, we are talking about a Trojan horse approach to treating multiple sclerosis. More information on this and other upcoming webinars is available at pirweb.org. Thanks for tuning in and have a great day.